So, good morning. Welcome to the Humanist community in Silicon Valley's Sunday Forum. My name is Matt Courtney, and I'm a recorder and a member of the board of the Humanist community. The Humanist community is a chapter of the American Humanist Association. Humanism is a reality-based philosophy of life that affirms our ability and responsibility to lead ethical lives of personal fulfillment that aspire to the greater good. We value freedom, health, happiness, fairness, compassion, and using science and reason to acquire and apply knowledge. If these words describe your thinking, we invite you to become a member of the Humanist community if you've not already done so. Membership forms are available on our website at humanists.org. If you are listening for the first time, welcome, and we invite you to continue listening to our weekly forums and other events. You can find all of our events listed on the website, humanists.org. Please aid us in continuing to present these forums by donating to the Humanist community. You can find out how to donate to our organization, again, on the website, humanists.org. Also, the treasurer has posted the address if you want to mail a check. He's posted the address in the Zoom chat. And a direct link to how to donate via credit card online. Our speaker today is Ron Garret. He's a software engineer by trade and is currently working on an easy-to-use cryptography software. He's got a lot of other credentials here that I'm not going to go through, but he's very, very tech-savvy. But today, he'll be discussing how we know what we know, part 5, the age of the earth. So this is part 5 or part 6 in a series, depending on how you count the series. I think this is part 5 for us. So Ron, go ahead and take it away.
Thanks. So the first installment of the series was actually given at ACSJ, what now seems like a long time ago. So it's part 6 in the series, part 5 here at HCSV. So let me do a little screen share here. Okay, so this is the 5th or 6th, depending on how you count, in what at the moment is a planned 9 talks about the history of science and how we know what we know. I've been putting part N of infinity into title slides because when I started this series, I didn't know how many parts there would be. And new topics keep popping up as I'm doing research for these talks. For a while, I thought there would be just 8, which I thought would be kind of cool because the infinity symbol looks like an 8 flopped over on the side. As I was putting this talk together, I realized I should probably add a chapter in thermodynamics. So that brings it up to 9, and so that neat bit of symmetry went out the window. But anyway, this installment is about the age of the Earth. It's a topic I got interested in when I started debating young Earth creationists on YouTube, but it turns out to be a really fascinating subject in its own right. This is the first topic in the series that is not foundational, that has to do with something other than basic physics or mathematics, the foundations of science. So unlike previous topics, there isn't an elegant equation or key experiment to serve as the climax of the dramatic narrative. It was just a number and a long story about how that number was finally arrived at after a lot of hard and dirty work. In this case, literally hard and dirty because a lot of it has to do with rocks. I also have to give a little disclaimer here and say that this is the first installment in this series about a topic about which I am not an expert. The first 5 installments are all topics that I've been studying either professionally or as a hobby for many years. But this is mostly about geology and biology, and on those subjects, I'm not an expert. Everything in this talk comes from information I found on the internet. I've done my best to filter out the fake news, but it's possible I still have some of the details wrong. So if we have any actual biologists or geologists in the audience, please don't hesitate to let me know if I've gotten things wrong. This is the context of the talk, the ones that have come before, and the 3 that I currently have planned for the future. So anyway, the scientific consensus today is that the Earth is 4.54 billion years old, give or take 50 million or so. or about the margin of error is about 1%. And to put these numbers in perspective, 50 million years, which is the margin of error on the age of the Earth, is about how much time has passed since the dinosaurs went extinct. And 4.5 billion is about a third of the time since the Big Bang. It took over 500 million years just for the Earth to cool to the point where it had a solid crust, but I'm getting ahead of myself. So 5.54 billion years is the right answer. But we've only known this for less than a century. And this is another thing that makes the story of the age of the Earth kind of unique. It's one of the questions that people would naturally think to ask about the world around them, but it's one where essentially no progress towards finding the correct answer was made until modern times. And in particular, the Greeks made no progress towards it. It's unusual because they made a lot of progress towards answering a lot of other natural questions that come up about the natural world. Aristotle took a guess and said that the Earth was infinitely old. Before 1800 or so, there were really only two guesses, one of which was Aristotle's. Both of them were badly wrong. Aristotle thought the Earth was infinitely old, which is actually not an unreasonable guess, and considered in relation to how long humans have been around to ask the question, is actually not that far off the mark. And the second very wrong guess was advanced by Bishop James Ussher in 1658, who traced through the genealogies of the Bible and concluded that the Earth was created in 4004 BC. The third wrong guess, which kind of marked the beginning of modern scientific inquiry into the topic, was made by William Thomson, also known as Lord Kelvin. And I'll get to that in a minute, but for now, let's start at the beginning. So like I said, the question of how old the Earth is kind of unique in the annals of scientific history because it is one where essentially zero progress was made until modern times. Aristotle just guessed that the Earth had been around forever, which, as I noted before, is not an unreasonable guess, especially given the data that Aristotle had to work with, which was essentially nothing. So that was pretty much the prevailing view for 2,000 years until this fellow, Archbishop James Ussher, made the first serious attempt at calculating the age of the Earth based on the assumption that the Bible was a literal and accurate history. He basically went through the whole Bible and added up all the generations of people recorded there and came to the conclusion that the Earth had been created on October 23rd, 4004 BC. This is the first page of the book that he wrote about this. I should note that Ussher was actually not alone in carrying out this calculation. A lot of other people did it too, including Isaac Newton, and they all came to similar conclusions. But Ussher's calculation was by far the most detailed, and his answer was by far the most exact, and so he's the one who gets the credit or the blame, depending on how you look at it. Now, if you're not a young Earth creationist, it's easy to scoff at Ussher's result. After all, it's off from the correct answer by 6 orders of magnitude. It's like saying that the distance between New York and Los Angeles is about 2 meters. But it's actually not as bad as it first appears. Ussher's work was essentially based on the assumption that the Earth's history coincided with human history, or at least with recorded human history. And on that assumption, Ussher's result was actually pretty close to the correct answer, because recorded history goes back about 5,000 or 6,000 years. So in a way, Ussher got the right answer, just not to the question he thought he was asking. But even during Ussher's day, there were already some hints that he might have gotten the wrong answer. There were these weirdly shaped rocks called, these are called snake stones. And these other weirdly shaped rocks called devil's toenails. And these other, these are more devil's toenails. And these weirdly shaped rocks called tongue stones, because people thought they were the tongues of dragons. And today, of course, we recognize these as fossils, but back then nobody knew what they were. The tungstone mystery was solved in 1666 by this man, Bishop Nicholas Steno or Steno, I'm not actually sure how to pronounce it, who noted that tungstones bore a striking resemblance to shark's teeth, and advanced the hypothesis that this is because they actually were shark's teeth, which of course is the right answer. This is a drawing from Steno's book on the topic. Steno's career is actually quite remarkable. In addition to being the first person to identify a fossil, he also did foundational work in anatomy and geology. He laid down some of the foundational principles of stratigraphy, which is the study of geological layers, which is a topic about which I could easily give an hour-long talk just by itself. But for now, I just want to point out one more thing about tongue stones and the idea that they are shark's teeth. Some of these tongue stones were really big, much bigger than the teeth of any known living sharks. So if tongue stones really are shark's teeth, then this one that's on your screen now must have come from a shark that was vastly larger than any shark living today. It is, in fact, a tooth from an extinct species called a megalodon. We don't have any complete megalodon skeletons, so I can't show you what this critter actually looked like because we just don't know. But we do know that it must have been huge. Here's another megalodon tooth fossil next to a banana for scale. This is our best guess about what megalodon may have looked like, probably about the size of a school bus. So over the next 200 years, the evidence that the Earth was much older than a few thousand years began to pile up. It started with megalodon teeth, but it didn't end there by a long shot. For starters, there was stratigraphy, the study of layers in the Earth. You can see these layers all over the planet, of course, but no one really undertook a serious study of them until the mid-1700s. Here are some more layers. These have been flopped over onto their sides so that they're vertical. Some of these layered formations are really striking. Anyway, no one took a serious study of them until the mid-1700s when this fellow, James Hutton, published a book called System of the Earth, Its Duration and Its Stability. I wasn't actually able to find an image of the book itself. This is an abstract that was presented to the Royal Society. But Hutton's main contribution was the principle of uniformitarianism, which is the idea that geologic strata should be explained in terms of uniform physical processes. The idea here is that the Earth was formed by physical processes that obey certain laws. And even if we don't know the details of what those laws are, whatever they are, they don't change over time. That's an assumption, of course, but the fact that we actually can explain geological strata this way is evidence that this assumption is actually true. But like I said, I could talk for hours just about stratigraphy, but let's go back to fossils for a moment because that evidence was starting to pile up too. In 1806, this guy, Georges Cuvier, was studying these fossilized bones that had been discovered in the Americas and concluded that they were the skeletons of creatures that didn't exist anywhere on Earth. But remember, we had some indirect evidence of extinction with megalodon teeth back in the 1600s. But this was the first time that a complete skeleton of an extinct creature had been discovered. This is a mastodon, which is a now extinct relative of the elephant and the woolly mammoth. This one is a giant sloth from South America. Here's a rendering of it next to a human to give you an idea of the scale. So by 1830, there was scientific consensus that the Earth was old, much older than 6,000 years, but no one knew exactly how old. The first person to take a serious stab at a scientific answer to this question was William Thomson, also known as Lord Kelvin, one of the pioneers of thermodynamics, which again is a whole separate topic in its own right. Anyway, he also got it badly wrong because he made one very stupid mistake and a whole lot of not so stupid mistakes, but at least he was on the right track. Kelvin, being one of the founders of the then cutting-edge field of thermodynamics, started with the assumption that the Earth started out as a ball of molten rock and calculated how long it would take for it to cool down to its present temperature. And the answer he came up with, was between 20 and 100 million years, which is wrong by about 2 or 3 orders of magnitude, but still a lot closer to the right answer than Usher's 6,000 years. So why did Kelvin get it wrong? Well, he made a whole series of mistakes, some of which were understandable given what he had to work with. So, for example, he started out by calculating the age of the sun, which he did on the assumption that it too was a ball of molten rock and that its energy came from gravitational collapse. Now, this is, of course, completely wrong, but we can forgive Kelvin for that because he didn't even know about atoms. Atomic theory wasn't finalized until about 100 years later. And of course, he didn't know anything about nuclear fusion, so you really can't fault him for that. Anyway, the answer he came up with for the age of the sun was about 100 million years, so he figured that the Earth couldn't possibly be any older than that. The second mistake that he made was that he didn't take into account the effects of convection, which, as one of the inventors of the field of thermodynamics, he really should have known better. Excuse me. Kelvin assumed that the Earth is a static sphere, and the only way that it can lose energy is to radiate it away into space. And of course, that's not true. The Earth has a very complicated structure. There is a solid inner core made of iron, and a liquid outer core, which is also made of iron, and then a liquid mantle on top of that made of all sorts of stuff. And then a solid crust on top of all that, which is where we live. And all those parts interact with each other in complicated ways to move heat around. But of course, Kelvin didn't know any of that. But he really should have gotten the convection part right. It wouldn't have gotten him that much closer to the correct answer because he was missing all this other stuff. But it would have made him look a little less foolish in the eyes of history. Anyway, how do we know that all this stuff that I've just told you is true? After all, we can't drill down to the core of the Earth and see that it's solid. We can't even get anywhere remotely close to that. The deepest hole that's ever been dug on Earth is called the Kola Super Deep Borehole. And this is a picture of the structure that was built in order to house the drilling equipment that was used to make the hole. It's named after its location on the Kola Peninsula near the border of Russia and Norway. It goes down about 8 miles. This is a picture of it, the top of the hole after it was all decommissioned after the fall of the Soviet Union. And I thought this is a really cool photograph because it's a very unassuming bit of plumbing, but it almost literally goes down to the depths of hell. It's the top of a hole that goes 8 miles down. At the top, it's just 9 inches in diameter. It gets a little narrower as the deeper you go. I think at the bottom it's 2 inches in diameter. I don't remember exactly. The temperature at the bottom is nearly 200 degrees Celsius, and the reason they had to stop at that point is that the rock at that temperature is not quite molten, but it's kind of soft and squishy and makes it impossible to drill through. But even at that depth, we've only gotten about 0.2% of the way to the center. And on the way to the center, there are literally thousands of miles of actual molten rock in the mantle and the outer core. So how do we know what's down there? Well, we know because of this woman, Dr. Inge Lehman, who was a Danish scientist from Copenhagen. Danish? Yeah, Danish. She was a seismologist, someone who studies earthquakes. And she noticed this weird feature of the data for something called a P wave, which is a kind of vibration in the earth produced by earthquakes. Interesting bit of historical trivia. The paper she published on this has the title P prime, which is to say it's the letter P with a little tick mark over it, making it the shortest title of any scientific paper ever published. And in fact, probably the shortest possible title because it's only 1 letter long. This was in 1936. Again, more than enough material here for an hour-long talk of its own. People make their careers as seismologists, so you can literally spend years studying just this little niche. There's so much interlocking evidence that to get it under an hour, at some point, I'm just going to have to throw up my hand and say, you have to either take my word for it or spend some time digging around on the internet on your own. Anyway, so the idea here is that earthquakes make different kinds of waves that propagate through the material in the earth. And these different kinds of waves travel at different speeds. And you look at the data for where these waves pop out. Oh, this is the cover, the first page of the paper that's here with the short title. And this is the figure, the first figure in that paper. Basically what you do, you look at where these waves pop out based on seismology data from seismographs that are located around the Earth. And you can't explain the data unless the waves are being bent and don't travel in straight lines. And you map out the way that these waves have to be moving, and you end up with these spherical structures where the waves inside the Earth, where the waves are being diffracted, and that's how we figure out what's inside the Earth. Anyway, so getting back to the question of how do we know how old the Earth is, there's all these lines of evidence, just literally mountains of it. Way too much of it for me to even scratch the surface. So let me just cut to the chase. How do we know that the Earth is 4.5 billion years old? So it's, back up a step. It's complicated. Calculating the age of the Earth involves many disparate lines of evidence: geology, seismology, radiometric data, even astronomy and cosmology. So how do we know? It's because of this rock. This is a photo of a gemstone called a zircon. This particular one is about 1/3 of a millimeter across, so about the size of a grain of sand. And it is the oldest rock ever found on Earth. It is 4.374 billion years old. How do we know that? It's because of a procedure called radiometric dating, which is based on the fact that radioactive elements decay at fixed rates. Every radioactive isotope has a characteristic number called its half-life, which is the amount of time it takes for exactly half of the atoms in a sample to decay. Excuse me. That number is always a constant for any given isotope, which is to say for any given atom with a particular number of protons and neutrons. And the ratio of radioactive isotopes in a sample is something we can measure. Again, this is something that people make careers out of, so hours of material here. There are lots of different kinds of isotopes that give you results over different kinds of timescales. For example, you've all probably heard of carbon dating, which uses a radioactive isotope called carbon-14, which has a half-life of 5,700 years. So that's good for dating mostly organic samples with ages measured in tens of thousands of years. Zircons and most other old rocks are dated using uranium, which decays into lead with a half-life of 1 billion years or so, depending on the isotope. So by looking at the ratios of uranium and lead isotopes in this rock, we can know how old it is. And so we know that the Earth must be at least as old as that. All this was figured out by a fellow named Arthur Holmes in the early 1900s. So this little piece of zircon puts a lower bound on the age of the Earth, but what about the upper bound? How do we know that the Earth isn't a lot older than 4 billion years? Because Earth, as we now know, is a very dynamic planet and material is constantly being moved around. In fact, the continents themselves are moving. That's a theory called continental drift or plate tectonics, which was first proposed by this guy, Alfred Wegener, in 1912. The most famous piece of evidence for this is the fact that the coastlines of Africa and South America fit together kind of like a jigsaw puzzle. This was noticed almost immediately as soon as the New World coastline was first mapped in the 16th century, but Wegener was the first to propose a theory to explain this. It took about 50 years before his theory was widely accepted. After all, the idea that the continents are moving around is kind of absurd on its face. But of course, it's actually true. Today, we have very accurate maps of the boundaries between the continental plates and how they move and the mechanisms that move them around. The boundaries are, we call them earthquake faults. Here's a picture of one. This one happens to be the San Andreas Fault, which those of you who live in California are intimately familiar with. So anyway, how do we put an upper bound on the age of the Earth since all this material is constantly being moved around and recycled? Well, we look at meteorites. Most of the meteorites that we use to make these measurements come from this place, which is Meteor Crater, Arizona, where about 50,000 years ago, a big hunk of rock measuring about 45 meters across, or half the size of a football field, smashed into the Earth and left this big hole, about 1,200 meters in diameter. And chunks of that meteor, which is called the Canyon Diablo meteor, are found all over the place in the vicinity of this crater. This is the biggest chunk that has ever been found there. That's basically what it looks like. It's mostly iron, so it looks like a big hunk of iron, but there are other materials in there as well. So we can do radiometric dating on these meteor fragments. And these meteors were formed at the same time as the Earth and the rest of the solar system. So that lets us put a date on the formation of the solar system, and that turns out to be 4.55 billion years ago. And so between the radiometric evidence, the radiometric dating evidence for these meteors, and the radiometric dating evidence of this zircon that's been found on Earth, we have a very tight bound now for the date of the formation of the Earth. And so we have a tight bound on the age of the Earth. That's the end of my spiel, but I have a couple of other things I want to show you if we have time. Do we have time? How are we doing for time?
We have plenty of time.
Okay. Then let me...
Please take more.
Okay. So let me... I'm going to go off script here and do a little ad-libbing and show you... This is a video of a lava lake in Vanuatu. And it's just a cool... Let me go back. Pause this. You can actually... This is essentially the exact same process, or one of the several processes that cause the continental plates to move around. This, of course, is on a much smaller scale and happening much faster, but it's essentially the same thing. And so you can get this visceral feel and see with your own eyes this process that is happening on a very large scale to create the surface of the Earth. If you want to go watch this for yourself, just go to YouTube and search for lava lake, and you'll find hours and hours of this kind of footage. It's really fascinating to watch. The second demo I wanted to show you is this little experiment that I did. I also put this on a YouTube video, so you can go back and review this if you want. I said, like I said, all of this came about when I started trying to understand young Earth creationism, because young Earth creationists believe the biblical account of creation and so believe that the Earth is 6,000 years old, which is just absurdly at odds with the evidence. And I started wondering how somebody could sustain a belief in something that is so much at odds with the evidence. That turns out to be another interesting story in its own right. But in the process of doing this investigation, I undertook this project to try to come up with an argument that the Earth is old that didn't require you to take anybody's word for it. So one of the counter arguments that creationists put or advance is that there's basically a big conspiracy in the scientific community to advance Darwinism and this godless lifestyle because we want to sin and surf the internet for porn or something without being accountable to God or something like that. I don't claim to completely understand all of the reasoning. I can just parrot back some of the words. So how do you answer conspiracy theory? Because now none of the data that I've given you is credible, because all of it relies on taking some scientist's word for it that they did the experiment that they claim to do. So I started wondering, is there a way that you can show that the Earth is old, or at least older than 6,000 years, just with evidence that people can see with their own eyes? And this is what I came up with. So you go to Google Earth and start out looking at the San Francisco Peninsula, and start out by convincing yourself because now we're trying to answer conspiracy theory here. So how do we have to first convince ourselves that Google Earth is not part of the conspiracy? So you just snoop around here until you find some familiar landmark, like maybe San Francisco International Airport, which is someplace that a lot of people have been. And you look at it and you reconcile that with your own personal experience of having been to this place. Well, this is refreshing a lot slower than it did when I did the dry run without Zoom running. Is that image clear yet? It's still refreshing on my screen.
It's clearing up, but it's pretty clear right now.
Okay. All right. This may end up being too slow if I have to wait for everything I want to show you to take that long to resolve itself, but we'll see how far we get. Anyway, so you look at the things in Google Earth that you're personally familiar with to convince yourself that Google Earth is not lying to you. And then you go here next to San Francisco International Airport, where there are these two lakes. There's this lake here called San Andreas Lake, and this one here called Crystal Springs Reservoir. And you notice a very unusual feature of these two lakes, which is that they're long and skinny and almost in an exact straight line. And if you look around at other lakes in the area, none of them are long and skinny and straight like this. And if you track that straight line up to the north, so here's the line, you go up north along that line, you get to another long, skinny body of water called Bodega Bay, which happens to be open to the ocean, so it's saltwater, but it's still a long, skinny body of water in that same straight line, and also this valley here in this same straight line. And you trace that straight line down towards the south, and you start to notice that there are more straight lines down here. So here, for example, yep, there we go. So here, where I'm moving my cursor, there's another straight line that you can see in the surface topography of this area. And all this, of course, is the San Andreas Fault.
You just barely see your cursor, sorry.
Oh, okay. Well, let's see here. So
I'm sure others can't.
Okay. So the line here is going at a 45-degree angle from the upper, more or less the upper left to the lower right. And I wish I didn't make the cursor bigger. But it's a pretty prominent straight line. Just go to the center of the very center of this image, and you can see this straight line here. Yes?
Yep.
And that just continues all the way up past the top of the screen and all the way down past the bottom. And I encourage you to actually just go on Google Earth yourself and go snooping around here, and you can zoom in to this and really get a good look at it. Anyway, I don't want to dwell too much on this. This is just to convince you that the San Andreas Fault is a thing that you can actually see with your own eyes. You don't have to take anybody's word for it that the San Andreas Fault exists. And then we go over here to Hawaii, which is the next part of the story. And the Hawaiian island chain, I'm going to wait for this all to resolve itself. This is the big island of Hawaii down here, and it's the first in a chain of islands that goes, again, up towards the upper left-hand corner of the screen. And I don't want to do too much zooming in and out here because of the time that it's taking for these images to resolve themselves. But if you go on Google Earth and look at this yourself, you'll see that the line of the Hawaiian Islands is almost exactly parallel to the line of the San Andreas Fault. And that's because Hawaii sits right in the middle of the Pacific Plate, which is moving up and to the left, towards the northwest. And the way the Hawaiian Islands are formed is that there's a volcano down here in the lower right-hand corner of Hawaii, which is Kilauea, the world's most active volcano. And it's spewing out lava, which falls into the ocean down here on the southeast coast of Hawaii and makes new land, which is then carried away by the Pacific Plate like a conveyor belt. And there's all kinds of evidence for that you can really dig into the details here. So, for example, one of the things that I show in the video is if you go down here, I gotta find the right spot. Yeah, it's over here. You'll see that there's a road here just along the coast. If you can see Holei Sea Arch, just inland of that, there's a road that parallels the coast. I'm going to zoom in on it. So here's the road. You can actually see some cars parked here. And there's a turnaround here where they don't let you drive any further. And the reason they don't let you drive any further is because a little further along the road, it's been buried underneath a lava flow. Wow. And the thing you observe here is that the lava that's on top of the road, which must be younger than the lava that's underneath if the road was built on top of, and the young lava is dark and the older lava is light. And that's because lava, when it's first formed, is very dark, and as it weathers, it becomes lighter in color. And so now we have this way of dating the lava flows on Hawaii just by looking at them. So the dark stuff over here is all young, and in fact, all of this stuff these are historical flows that all have happened in the last 100 years or so. They're all incredibly well documented. There is even video of some of them. If you go to Hawaii, you'll find signs that say, this lava flow happened in 1973, and that one happened in 1989 or whatever. And you can see a lot of dark material here this is Mauna Loa, which is also still an active volcano. And one of these days it will erupt and almost certainly destroy the town of Hilo, which is over here on the east coast of the Big Island. But as you go further to the northwest, what you find is less and less of this dark young material. The next island is Maui, and there's just a little tiny bit of dark flow down here in the southern corner, which is from an eruption that happened in the 1700s that created a bay down here called La Perouse Bay. So here's that eruption that created La Perouse Bay. But there's almost no more of this young, dark material. So we know that Maui must be older than the Big Island. And as you go further and further to the northwest, you find less and less dark material and more erosion until by the time you get to Oahu, there's very little evidence if there was ever any volcanic activity here at all, except that you do find little remnants of volcanoes, like this is Diamond Head down here, which you can tell was a volcano at one time. But it's all been eroded away. And so just by looking at this, in Kauai, there are no more, you have to look very carefully to find evidence that there was ever any volcanoes here. Here's a little hint on the last island in the chain called Niihau. Just up here, there's the very last remnants of a volcanic caldera making this little crescent-shaped island that's just almost completely eroded away and fallen back into the sea. And all this is evidence that the way that this was formed is there's a hot spot here, this volcanic hotspot with lava coming up from the mantle that forms young material over here. that then gets carried away by the Pacific plate moving up in this direction, where it gets eroded away and eventually sinks into the ocean. And the rest of the chain here, these are all underground seamounts and coral atolls, but they go on for 3,000 miles. And so this process has created, it actually goes on for further than that, because it actually makes this little turn here and then goes up to the north, but that's another story. Just the straight part is 3,000 miles long. And you can do the math on how fast this would have had to have been moving in order for all that to happen in 6,000 years. And the net result is that it would have to be moving at about half a mile a year. And if the Pacific plate were moving at half a mile a year, you could measure that with a GPS. And the location, you wouldn't be able to fly there. You wouldn't be able to navigate there because Honolulu Airport would be moving half a mile every year, and it isn't. The actual rate of movement is about 10 centimeters a year, so it does move, just very, very slowly. And you do the math on the actual rate of motion, and it works out that just the straight part of the Hawaiian Island chain took 300 million years to form, which is less than 10%, of course, of the total age of the Earth. This has never actually convinced a younger creationists that they were wrong. They come up with all kinds of excuses why they don't buy this argument. But again, that's a whole other story. That is all I got. If you still want me to go on, I could try to do a little song and dance.
Well, do you want to start taking questions?
Yeah.
I think we're at a good point for questions. So please use the raise hand feature in Zoom if you want to ask questions. Let me see if there's anything on Twitch. I think the only comment on Twitch, now I can't find, oh, here it is, by Kvass Residue, says he wants to throw pennies down, and he's talking about the lava lake. Looks like a wishing well, I guess. Probably don't want to do that.
The video clip that I showed is part of a much longer documentary about this particular lava lake and the scientists who study it. And there is a video clip of a guy trying to get to the edge of that lake to get a sample of fresh lava. And he's dressed up in this this moon suit that looks like a full-on spacesuit. And he's climbing up the side of the wall of the lake because the lake has formed one of these cinder cones around it. And the video is being taken by a camera on the rim of the crater. So we're looking down on him. He's very tiny. He's scrambling, trying to get up the walls of the lake. And the lava level is rising, but he doesn't know this. It's an incredibly dramatic scene because if you can throw a penny into a lava lake and it will melt instantly. In fact, you can throw a rock into a lava lake, which has a much, much higher melting point than a penny. Because pennies are made of zinc, you can actually melt a penny with a blowtorch. Because that's what the lava is. It's molten rock. It is unbelievably hot. I actually had the good fortune of being on the Big Island of Hawaii during one of the episodes where fresh lava was covering up part of Chain of Craters Road. And so you could just walk along the road right up to the fresh lava. And I could not get any closer than about 10 feet before it began to be painfully hot, to the point where I felt like if I stayed for more than 5 or 10 seconds, that I would actually start to burn. It's indescribable. If you ever have a chance to experience being close to hot lava, I encourage you to take advantage of it. It's something that cannot be described. It really has to be experienced.
Okay. Well, it looks like we have a question from Alex Andorcena.
Yeah, I actually put it on the chat, but when you were talking about the age of rocks and so on, do we have a theory about why a given atom has a certain rate of decay? Is that just something
Yes.
we measure and assume is correct?
No, that's something that's actually quite well understood. It's a consequence of quantum mechanics. I mean, we don't understand it in detail, but the basic underlying principles are well understood. So atoms are these quantum objects, and so they obey the basic rules of quantum mechanics. And the basic rules of quantum mechanics are that the world is described by this thing called a wave function that doesn't describe the way the world is, but describes the way the world could possibly be and assigns different probabilities to the different ways that it could possibly be. And then when you do a measurement, one of these possibilities, the wave function collapses, and one of these possibilities turns out to be real for some sense of real.
I mean, if you could describe the nucleus of an atom, and some physicists could tell you what the half-life of it would be.
In principle, yes. In practice, the math turns out to be much too complicated. We can accurately model very simple atoms and very simple nuclei. So the hydrogen atom, for example, is basically completely described by quantum theory. Beyond that, I don't actually know how much progress has been made. But by the time you get to radioactive nuclei, those are so complicated that they are well beyond our current capability to actually carry out the math, and probably beyond our capability anytime soon. It'll probably the only hope of actually doing the math is by getting quantum computers to actually work. Because that's the thing that makes quantum computers cool, is that they are capable of doing this particular kind of very complicated math that comes out of quantum mechanics that can be done in principle, but not in practice using regular computers because it's just too complicated.
Okay.
So for our actual knowledge of half-life, we just have to measure them.
That's what I thought. But there is a theory that covers it.
Yes. So what the theory tells you is that the half-life that you measure has to be constant. So that's the thing. The theory is what answers the objection of how do you know that the half-life was the same a billion years ago? Maybe that's changed. And the answer to that is that's possible. But in order for a half-life to change, it means that there has to be something fundamentally wrong with our understanding of quantum mechanics. And quantum mechanics is the best confirmed scientific theory ever. There's never been an experiment done that is at odds with the predictions of quantum mechanics. And so for quantum mechanics to be wrong, that would be the single biggest breakthrough in the entire history of science. It's extremely unlikely that quantum mechanics will turn out to be that wrong. And so, we are as certain about the constancy of half-lives as we are certain of anything in science.
Okay, one other question that kind of crossed my mind is you gave a diameter of the Diablo comet, the meteor, the thing that created the Devil's.
Yep.
That
45 meters.
Right. Well, I'm curious about the size. Is that when it hit, or was that the size?
That's the size when it hit.
Okay.
And the way they know that is by looking at the size of the crater that it left and doing the math on how much energy it takes to make a crater that size, and then figuring out how big an object you need to carry that much energy.
The angle that it struck at.
That is beyond the limits of my knowledge. Okay. You have to look that up.
All right, thank you.
Uh-huh.
All right, we got Herman Winnick. You're going to have to unmute yourself. There you go.
Oh, hi, thank you. Yes, the rules of quantum mechanics predict that nuclei are arranged in shells of neutrons and protons, much like the orbiting planets around the sun and the electrons around the nucleus. But the nucleus itself is made up of shells. And according to those who believe in the biblical age of the universe, everything was created 6,000 some odd years ago, that some of the materials created at that time would have existed in these islands of stability associated with nuclear.
So I don't know what happened, but I just lost Herman's audio.
Yeah, so did I. He's not on mute, so it's something on his computer. Uh-oh.
Can you hear me now?
Yes.
Yep, you're back.
Okay.
So I lost you at Islands of Stability.
Okay, the islands of stability extend in shells where nuclei are particularly stable. So if you go through the nuclear charts and go from hydrogen to lead to gold to uranium, there are the so-called transuranic elements, which can be made now in accelerators by bombarding the heavy particles like radium, uranium, whatever, and temporarily form a heavier nucleus, which then decays very rapidly. And those decays come along with the emission of a radioactive particle like proton, neutron, electron, or alpha particle. And in fact, the alpha particles are particularly favorite ways in which extremely heavy nuclei, which are unstable, reach stability by throwing out the excess number of neutrons and protons in the form of an alpha particle, which is a helium nucleus consisting of 2 protons and 2 neutrons. Anyway, those who believe in the biblical age of the universe would expect that these closed shells would have existed at that time, and there would be so-called islands of stability in transuranic elements, very ultra-heavy elements beyond the uranium and lead that we have now, where the lifetime would be particularly long. It would still be unstable, but their lifetimes would be comparable to the biblical age of the universe, so that some of them would still be around. Anyway, all that is background to setting the stage for searching for these super heavy elements rather than making them in accelerators, but finding them naturally existing in the earth. So a particular scientist named Robert Gentry at Oak Ridge National Laboratory back in the 70s or 80s spent his career, he was a fundamentalist Christian and believed in the biblical age of the earth, and he went around the world seeking evidence of the existence of these closed shell super heavy elements, one of the characteristics of which is that they would emit a particularly energetic alpha particle. And that particularly energetic alpha particle would damage its local surroundings according to its range. And if it was particularly heavy, it would create a damaged sphere around it, which was particularly large, a so-called giant halo. So he finally found what he considered to be evidence of this in giant halos in a material called Madagascar mica, which he found, I think, on the island of Madagascar. And he was jubilant that he had evidence of the biblical age of the universe, which was his objective. So he took these back, and to try to verify that there were these super heavy biblical age elements in these samples, of which he had only half a dozen or so. And he took them to various accelerators, such as a proton linear accelerator in Florida, and bombarded them to excite their electronic structure and watch for decays, which would be predicted by atomic theory and quantum mechanics. And lo and behold, he found that there was some evidence by the excitation of these samples of Madagascar mica that coincided with the predicted energies of the alpha particles. And he said, my God, not only do I have evidence from the giant halos, which you could see in a microscope, but I also have evidence from exciting these elements that they, in fact, existed. So this created a big stir in the physics community. Most physicists were very dubious about this because there aren't many fundamentalist Christians in the physics community. So because of his association with a government laboratory at Oak Ridge, and they put pressure on our laboratory here at Stanford, SLAC, where we make very energetic X-rays using accelerators, and these X-rays can probe the atomic and nuclear structure of atoms by shining X-rays of the appropriate energy on them and looking for the decays. So they persuaded us to run the accelerator in a particularly different way so that it would enhance the probability that these elements could be detected. And about 4 or 5 days was devoted to running in that special way. And they brought these samples. These were very precious samples because the only way they had looked at them in the past was to expose them to very damaging proton beams, which destroyed them. And you could get some evidence from that, but you also destroyed the sample. And there were very few of these examples of the proof of the age of the universe. But X-rays are less damaging. So they brought these samples to Stanford, to the SLAC, the Stanford SLAC National Accelerator Laboratory, and shined X-rays on them, particularly tailored to have the energies necessary to excite them and then look for the consequent decay, because you promote an electron to some higher energy level and look for that electron to decay and emitting a characteristic X-ray, which would be predicted to be associated with the atomic structure of one of these primordial super heavy elements. So we were running the accelerator that way over a weekend, and this guy back in Oak Ridge was certain that they would find evidence confirming his belief in the biblical age of the universe. And he kept calling up every day, several times a day, to find out how things were going. And he called up on a Sunday once when we were running, and the people told him that there was a problem with the accelerator and it was down, to fix it. And this was on a Sunday. And this fundamentalist Christian who has supplied these samples, named Gentry, was shocked. He said, "You mean you're running the accelerator on a Sunday, God's day of rest?"
I was just thinking to myself, you're calling on a Sunday, God's day of rest?
That's right. Well, we were running the accelerator on a Sunday, which is even a larger sin. He says, "What did you expect?" Anyway, they ran this thing through the weekend and beyond, fixed the problem and got the running in, and were able to set an extremely low limit on the possible existence of these super heavy elements. So I think it is no physics experiment that I'm aware of that confirms the biblical age of the universe. We had some excitement about that here at Stanford back in the 1980s.
Yeah, I know nothing about this, and I would have predicted that outcome, not just because I would predict the outcome of any experiment trying to confirm the biblical age of the Earth to come out negative, but that particular one, because I've never heard a young Earth creationist bring it up. The arguments of young Earth creationists tend to follow cycles of fashion. They come up with some argument and it gets debunked, and they come up with something else and it gets debunked. And so there's always the argument du jour that hasn't been debunked yet. And that wasn't it. But it seems to me that they've got this exactly backwards, that if there were naturally occurring elements in these islands of stability, that what you would expect to find is samples of the transuranic elements in the islands of stability, not the decay products of having them decay, because you'd expect them to be, because they're long-lived, you'd expect them to survive at least 6,000 years. So they should still be around. So you should be able to find actual samples of them, not just their decay products. But I'm not a young creationist, so what do I know?
This guy believed that he found the decay products and was now looking for evidence of the samples themselves.
No, I understand that, but I don't understand the theory that he's trying to advance. It seems to me that the evidence that he was looking for would undermine what he was trying to prove. But again, I don't know, and
yes,
frankly, don't much care. But it's an interesting story.
Check it out. You may find it on the web. Biblical Age of the Universe. Robert Gentry is the name of the scientist.
Yeah, I found it, and I also found that you're apparently quite well known in this field. And by the way, I should also, my father's waving his hand. My father is a nuclear engineer, so he's actually a domain expert here. So, Abed, do you have something that you wanted to add to this?
No, I think I've told the whole story, but I encourage you to look it up. Where did you find it? What did you put into Google?
Oh, I just put in, what did I put in? I think I just put in the guy's name, Roger Gentry, Young Earth Creationism.
Yeah, Robert Gentry.
Robert,
yes.
Yeah, and I got this, there's this fairly extensive article at Tufts that came up. Is there really scientific evidence for Young Earth? And it's quite long. I'm going to read it once we're done here. But I also found your Wikipedia page.
Well, many lies in that one. Don't believe it.
It's all fake news, huh?
Right.
I see. Yeah, Yuri has his hand up.
Yeah.
There you go.
By the way, I'm talking to you from Oak Ridge right now. The question I have is there an explanation how the writers of the Bible came up with the age of the universe?
The writers? Or the writers of the Bible didn't come up with the age of the universe.
Well, how did they come up with those 6,000 years?
James Ussher came up with it by tracing through the genealogy. So if you read Genesis in particular, there are and a few of the other books, there are these genealogies where they say this guy lived this many years and begat that guy, and that guy lived this many years and begat this other guy. And you just trace out the entire human family tree and add up the numbers.
But they must have had some thought about the longevity of each of these guys.
It says the Bible,
they relate to one another.
the Bible. That's exactly the information that the Bible gives you.
Okay.
So Adam lived 130 years and begat a son, and the days of Adam after he'd begotten Seth were 800 years. And Seth lived 105 years and begat Enos. And Enos lived 90 years and begat Canaan. He lays it all out for you in excruciating detail.
Okay. Jim has his hand up, but he's not finding the raise hand feature. Ask him to unmute.
Am I unmuted?
Yep. Go ahead.
Okay. Herman, I wanted, was there another explanation for the halos in the Madagascar mica?
Herman, you got to unmute yourself.
What's that?
There we go.
Yeah, there was just another transition in the nucleus or the atom, I don't remember which was had a particularly long lifetime and was rather rare, but was there, still not observed and not as an alternative explanation. And so you have two explanations of these giant halos and the emission of these alpha particles. One is with conventional nuclear theory, and the other was with the biblical age of the universe. You go with what you want, okay? But there was a simpler physics explanation of the previous results, the giant halos in particular.
Thank you.
All right. Do we have any other questions, or we can go move on to a general discussion? I don't see. Oh, there we go. Alex and Senna.
Yeah, I was wondering about Earth tectonics. Do other planets have that? Does Venus have tectonic plates? Do we know?
For the most part, no. We do know, and the answer is no. Venus in particular, I'm not 100% sure. Mars does not, and the Moon does not. Europa is interesting because it's covered with water, so it has an ice crust that's a couple of miles thick, and there are ice plate tectonics on Europa.
Okay.
But in order to have plate tectonics, you have to have a planet that's mostly molten. So you have to have active volcanic activity, and so first of all, you have to have a planet that's solid, and that rules out all the gas giants. So there are only Mercury, Venus. There are only 4 rocky planets, and I'd have to look up on Venus. I'm pretty sure the answer there is no.
Yeah, I'd read somewhere that, and it might have just been speculation, that Venus has a thicker crust than Earth, and therefore.
Yeah, I don't know about Venus offhand. I'd have to look it up. There are some of the moons of Jupiter and Saturn that get heated up from tidal forces from the planet that they're orbiting, and that generates enough heat to cause volcanism. So, for example, on Io, there are sulfur volcanoes, and so Io might have plate tectonics as a result of that. Again, off the top of my head, I just don't know. But I'm sure the answer is just a Wikipedia search away.
Yeah, I was thinking also, if you want to start rejecting the evidence as being put there to fool us, you've lost control completely. You can't prove anything if you assume that your memory is wrong or that false evidence has been planted, unless you can prove that the evidence is false.
Yeah, well, there are 2 kinds of false evidence. There's false evidence that is the result of a human conspiracy to plant false evidence, and that's always a plausible hypothesis because that's actually a thing that happens. Look at QAnon. Right? But there's another kind of false evidence, which is a theory that's occasionally advanced by young earthers, which is that the universe was formed recently, but in the state that it would have appeared to be 6,000 years ago to make it appear as old as it is. So, all the stars are where they seem to be, but when the universe was formed, God set it up so that the light from the stars was already in transit to Earth, so that just 6,000 years later, the light from these stars that appeared to be millions of light years away gets to us. And that kind of hypothesis is one that you can never rule out on the evidence. The reason that science rejects that kind of hypothesis is because it's unfalsifiable. So you can have it's part of a whole family of hypotheses that are usually caricatured under the label last Thursdayism. Because I can say, well, maybe the universe was formed last Thursday in the exact state that it appeared to be in last Thursday. That's another hypothesis that can never be ruled out on the evidence. And of course, there is one such hypothesis for every instant in time in the past. And at most, one of them could possibly be true, if any of them are true. And so if you just pick one at random, the odds that you'll get the right one are indistinguishable from 0. And so almost certainly any one of those hypotheses are false. And so they all get rejected.
Thank you.
Okay, I'm going to go back to Herman. If I can get that button. There we go. Should be able to unmute. Nope. Try it again.
Oh, there it is. Okay. Associated with the age of the universe is, of course, the ideas of intelligent design as opposed to evolution. And the comment I like to repeat, which I think I've mentioned before, is that the main reason against intelligent design is that no intelligent designer would wrap the prostate around the urethra. And I'll leave you with that.
Yeah, I'm certainly beginning to discover more and more items of very unintelligent seeming design in my own body as time goes by.
Okay. Oh, we have Fran and Jim.
One of the most dramatic areas I've seen that would really confirm the ancient age of the Earth was at the Arches National Park in Utah, where you can see 23 layers of different colored sands where ancient oceans filled, left residues of one color sand, evaporated, and winds blew in different color sand. Then the oceans returned, deposited another layer, and you can see these layers one after another, 23 of them. And they took millions of years each to form, and it's really very dramatic. And if you're a believer, it's very easy to convince you that these are evidence of a very ancient Earth.
Now, the YECs would just say that all happened during Noah's flood.
What was that?
The young Earth creationists, the answer that they would give to that is that all of those formations were created during Noah's flood.
Oh, yeah.
Along with the Grand Canyon.
Yes.
So you get like layers in a single flood event? That doesn't make any sense.
Yes, I know none of this makes sense. Like I said, all I can do is parrot back the words. Right. But they have this theory called hydrological sorting, where you have this catastrophic flood that comes in, and you got all this water that churns up all this material, and it all gets sorted into layers as the material settles out of the water, and it all gets stacked on top of each other nice and neat in order to produce all of the geological formations that we see today.
I received a beautiful book on the Grand Canyon with these wonderful illustrations, and it was produced by a young earther who's accredited the Grand Canyon, of course, to the Noah's flood. But one of the great pictures in it showed a U-bend in the canyon on the same page as accredited to a great flood. Can you imagine a flood creating a U-turn in a canyon?
Yeah, so this is something I happen to know something about because I've watched a video addressing exactly that issue. And the counter argument to that is they basically set up a little tiny model in a sandbox, basically, that they spray down with a hose. And I forget exactly the details of how they managed to set this up. But if you get a tiny trickle of water moving in exactly the right way, then the surface tension of the water will cause it to bend around and make one of these U-bendy kind of channels. And they point to that and say, see?
I'm learning more and more about theories for young Earth creationism than actual scientific creationism or scientific age of the theories in this particular talk.
Yeah, sorry about that.
I have Susan Shallett and looks like Roy. You have to unmute. There you go.
Yeah. I've heard, I don't know the parameter, but there's several parameters that if they were off by some part in 10 to the 10th or something like that, the weight of the electron, blah, blah, blah. But there's one parameter, I forget the name of it, is if it's 1 part out of 10 to the 100th or above, whatever that number is, 1 part out of that, we would not be here. I forgot the name of it. So
my guess is that you're referring to the fine structure constant.
yeah.
And 10 to the 100th is almost certainly a radical overestimate.
Yes.
Because that goes well beyond the limits of what could be measured, even in principle, with arbitrarily advanced technology, beyond the limits of what quantum mechanics would actually allow you to measure. But yeah, there are these fine-tuning arguments that people point to and say, look, if any of the fundamental constants of nature were different by a tiny amount, then you couldn't have stable atoms, and therefore you couldn't have us. And therefore, this is evidence for God. And my answer to that is that even if you accept this argument at face value, which I don't, I think there are convincing arguments against it, but even if you accept it, all that gets you to is something that did this fine-tuning, which could have just been luck, or could have been an agent of any sort. It gets you nowhere near any particular deity. It certainly doesn't get you to the God of the Bible, and it certainly doesn't get you to young Earth creationism. But all of these arguments are advanced by particular strains of evangelical Christianity, and they're all in service of an ultimate agenda of trying to convince you that Christianity is true. And this particular argument, even if you accept it, I don't see how it gets you anywhere close to the idea that the proposition that Christianity is true or that the Bible is true.
Yeah, I don't know enough about that physics and everything there, but is it possible that with changes to these numbers that, you wouldn't get atoms, but you may get some other kind of stuff that the universe would be made out of? Or
Yep. So this is now at the very limits of our understanding of fundamental physics and solidly in the realm of speculation. But there is some evidence that the universe that we perceive, which is to say the classical reality that we live in day to day, that's not the only reality that there is, that there are, possibly, for example, parallel universe that are similar to ours, but different in certain ways. And in particular, every time there is an interpretation of quantum mechanics called the many worlds interpretation, that says that every time you do a quantum experiment, and you don't actually have to do a formal experiment, anytime any physical interaction happens that involves some kind of a quantum outcome that has more than one possible outcome, that all of the outcomes actually happen, that the universe splits or peels apart or something, and that the end result is you get this mind-bogglingly vast proliferation of universes, of which ours is only one. And it sounds completely insane. And the caveat that you have to keep in mind is that plate tectonics also sounded completely insane when it was first proposed, but it actually turned out to be true. And many worlds is a possibility that cannot be ruled out based on our current understanding.
yeah, but is it like something that we could actually prove? Is it falsifiable?
Well, not given our current understanding.
Yeah.
But it's possible that there's something that someone hasn't thought of yet that would allow us to do an experiment. All of these interpretations of quantum mechanics, the reason that people are still arguing about them is because nobody's come up with a way to test them. They're all trying to explain the structure of the math, and everybody agrees on the math, and so everybody agrees on what the outcomes of the experiments are going to be, and so no experiment can distinguish between these various interpretations. There's one exception to this. There's one interpretation called GRW collapse theory. I'm not 100% sure I got the initials right. I'd have to look this up. Pretty sure it's GRW, but I have to look it up to be sure. That one actually does make a prediction that at some scale, you can start doing quantum experiments on larger and larger systems. And this particular theory predicts that you will get to some scale where you will see a transition from quantum behavior to classical behavior, where you can no longer produce quantum behavior. And it doesn't make a firm prediction about where that transition will happen, only that it will happen somewhere. And so far, all of the experiments that we're doing on larger and larger scale quantum systems, that prediction has failed to be borne out. And some of the systems that we're doing experiments on now are pretty freaking big, almost to the point where you can see them with your naked eye, almost.
Wow.
Yeah. This is one that you can't really rule out just yet, but I'll give you long odds against.
Okay, I'm going to go ahead and end the Q&A, and we'll just go to general discussion.